Hi dear students, today now we'll discuss the molecular orbital structure of furan. This is also one of the very important topic in your exam. This is also for 4 marks or 5 marks, and it is usually there for the final year BSc students in chemistry. So furan is an heterocyclic compound as we discussed in the last classes. So furan, its molecular formula, furan is C4H4O, and if you see the structure, this is the structure of furan. It is an heterocyclic compound containing and one oxygen as a heteroatom. So here we have carbon and oxygen. Both carbon and oxygen are sp2 hybridized. Both of them are sp2 hybridized. Yeah. For carbon atom, the atomic number of carbon is 6. Its electronic configuration in ground state is 1s2, 2s2, 2p2. The same electronic configuration in excited state for carbon atom, 1s2. This is the valence orbital, second orbit. So here 2s, 2p. In excited state, one of the 2s orbital will shift to the 2p orbital. So it will be 2s1, 2p3. If I put the box of orbitals for these orbitals, and inner orbitals like 1s orbital does not involve in hybridization, hence I am putting box for 2s and 2p orbitals. This is for 2s, and in case of p orbital there are 3 subatomic orbitals. That is, in case of 2p, one is px, py, pz, that is 2px, 2py and 2pz. Yeah, here in case of 2s there is one electron, in 2px there is one electron, 2p1 1, there are 3 electrons. Okay, as it is undergoing sp2 hybridization, 1 2s orbital and 2p orbitals will be undergoing hybridization, that is giving us 3 sp2 hybrid orbitals, and the remaining one is an unhybridized p orbital. P unhybridized p orbital. Okay, and for oxygen atom, the atomic number of oxygen is 8, and if you write the electronic configuration in ground state, that is 1s2, 2s2, 2p4, and same electronic configuration of oxygen in excited state is 1s2, 2s, 2p. Here the same thing happens, 2s1, 2p5, 2p5. Yeah, if I put the box for these orbitals 2s and 2p, 2s, 2p. Among 2p there is 2px, 2py, 2pz. In case of 2s, 1 electron is there. Here 1, 1, 1. In excited state, it is against Hund's rule. It does not follow the Hund's rule. That's why in the last 2 orbitals we have pair of electrons. And if you see here also, it is also undergoing sp2 hybridization, hence 2s orbital and 2p orbitals, 2s 1 orbital and 2p orbitals will undergoing hybridizations. So here these are become 3 sp2 hybrid orbitals. And there is also one unhybridized p orbital. Yeah, unhybridized p orbital. If you write this electronic status, here you will writing for carbon atom, it is actually showing sp2 hybridization, and we have here, yes, 3 sp2 hybrid orbitals with unpaired electron, with an unpaired electron in each, and there is one unhybridized p orbital which is containing, that is also with a unpaired electron, with an unpaired electron. Yes, for carbon atom, that is also sp2 hybridized. Here you can see one of the 3 sp2 hybrid orbitals, sp2 hybrid orbital containing pair of electron, and the remaining 2 are unpaired. So 3 sp2 hybrid orbitals, among which 2 orbitals, 2 sp2 hybrid orbitals with an unpaired electron, and one of the sp2 hybrid orbital is containing a pair of electron, with pair of electron. This is the electronic system, electronic status of the carbon and oxygen in the Furan ring. Now we will discuss the bond formation. That is, we are going to write the molecular orbital structures. First we will write the molecular orbital structure for the formation of sigma bond, and later we will write the molecular orbital structure for formation of pi bonds for the Furan atom. Now we'll write formation of sigma bonds. Sigma bonds. In the structure you can see there is a sigma bond between carbon and carbons, and also carbon and oxygen, and each carbon is linked to the hydrogen atom. There are 3 types of sigma bonds, that is carbon-carbon sigma bond, carbon-oxygen sigma bond, and carbon-hydrogen sigma bond. Let us see all that. See formation of sigma bonds. You know, as both carbon and oxygen are sp2 hybridized, so then the sp2 hybrid, if it is sp2 hybridized, then the geometry will be trigonal planar. The geometry is trigonal planar. You know the geometries earlier in hybridization classes. So now let me write the sigma bond formation. So there are 4 carbon atoms. So 1 carbon, 2nd carbon, 3rd carbon, 4th carbon, and there is an oxygen atom. Yeah. And each of the carbon and oxygen are sp2 hybridized, hence they will get the trigonal planar geometry. This is the geometrical shape of the orbitals for both carbon and oxygen. So here what happens? Each of the sp2 hybridized orbital of carbon containing unpaired electron. So each of them are containing a single electron. And this electron, or this orbital, especially orbital, overlap with the sp2 hybrid orbital of the another carbon. So it is get paired up and forming a cc sigma bond. Cc sigma bond. You can see this overlapping is, this is an sp2 hybrid orbital, and this is also sp2 hybrid orbital of the this carbon. So this is the sp2 overlapping, that is leading to the formation of carbon-carbon sigma bond. The same thing here also, this carbon is still having one more orbital with an unpaired electron, and that overlaps with another hybrid orbital, sp2 hybrid orbital for another carbon atom, and forming a, this is also sp2 overlapping, forming a carbon carbon sigma bond. And here also carbon, one of the, even you can see in oxygen there is two sp2 hybrid orbital, sp2 hybrid orbitals with unpaired electron. Yeah, these both are unpaired, and another one is pair of electron. Yeah, so the sp2 hybrid orbital containing unpaired electron will overlap with the sp2 hybrid orbital of the carbon with the unpaired electron. So this overlapping is also sp2 overlapping and forming a carbon oxygen sigma bond, CO sigma bond. The same thing here also, carbon carbon sigma bond, and here carbon oxygen sigma bond. So here it is a carbon, this is also sp2 overlapping, then this one is also sp2 overlapping. This is how we can form the carbon carbon sigma bonds and carbon oxygen sigma bonds. And still each carbon containing an hybrid orbital, sp2 hybrid with a lone pair of electrons. You can see all the 4 carbons. So this will overlap with the s orbital of the hydrogen atom, forming CH sigma bond. This overlapping is, one of the orbital is sp2 hybrid orbital and another one is s orbital of the hydrogen. This overlapping is sp2 s overlapping. So please remember, sp2 s overlapping will lead to the formation of, result in the formation of carbon hydrogen sigma bond. Here also the same thing happens. So this hydrogen s orbital and sp2 hybrid orbital of carbon atom will overlap, forming CH sigma bond. Here also the same thing happens, CH sigma bond. Now oxygen is free. Here one more carbon. Yeah, actually this is the molecular orbital structure of furan for the formation of sigma bonds. And if you see its inferences, you hear the carbon carbon sigma bond and carbon oxygen sigma bond, carbon carbon sigma bond, carbon oxygen sigma bond. These both are formed by sp2 overlapping, sp2 overlapping, and the remaining carbon bond is carbon hydrogen bond. So carbon hydrogen sigma bond, this one is formed by sp2 hybrid orbital of carbon and hybrid s orbital of hydrogen, that is sp2s overlapping. This is very important. This is the molecular orbital structure of furan for the formation of sigma bond. After this, I hope you see, this is very important, you should mention, and you should mention these also, and you do not need to write these things electronic status in the exam, because they are only ask for the, they definitely ask only for the molecular orbital structures. If you write this one also, no problem, but this much you at least you need to mention these things and these things. Even if you write like this point wise also, you will definitely get a full marks, because you should mention what is happening perfectly. Okay, the electronic system, electronic status of carbon and hydrogens, sorry, this is for oxygen atom. Okay, and here the formation of sigma bond. Please remember, carbon carbon sigma bond and carbon oxygen sigma bond are formed by sp2 overlapping, and carbon hydrogen sigma bond is formed by sp2s overlapping. After this, we will now write the molecular orbital structure for the formation of pi bonds. Yeah, and please remember, this is also very important, still the oxygen is containing a lone pair of electron. in the same plane of the sigma bond. So this is a non-bonding pair of electrons. They do not involving in any kind of bond formation in the furan for this compound. So please remember, these are a non-bonding pair of electrons of oxygen in the furan. They do not have any functional aspects in the formation of the structure. Okay, so they will have some, definitely they have some reactive properties that we'll discuss in the next class. So please remember, the oxygen is still containing a lone pair of electron which is not involved in the bond formation, hence it is a non-bonding pair of electrons or lone pair of electrons of oxygen. So please remember, each carbon and oxygen are sp2 hybridized, and in carbon, three all the sp2 hybrid orbitals are containing unpaired electrons, and there is one unhybridized p orbital with a single electron or unpaired electron. For oxygen, among three sp2 hybrid orbitals, two sp2 hybrid orbitals are forming are with an unpaired electron. Those are forming sigma bonds. There is still one more hybrid orbital with a pair of electron that do not form any kind of bond. That is a non-bonding pair of electron. But still we have a one more p orbital, that also I should mention here. I'll write here now. One unhybridized p orbital is also present in oxygen with, see, that is also with pair of electron, with pair of electron. I think I forgot to write here when I was talking about this. Please you mention it. Okay, you can now take the screenshot of this one because that is very important. Even if you write this much also, you will definitely get a full marks. And after the formation of sigma bond, now we will see the formation of pi bonds. Students, formation of pi bonds. Okay, so you know, always pi bonds are formed after the formation of the sigma bonds. So when sigma bond is formed, if you write the bonding structure, this is equivalent to this structure. There is a carbon-carbon sigma bond. Yeah, these all are sigma bonds, and also it has bond with hydrogen, 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 and this still oxygen is carrying a pair of electron in one of the sp2 hybrid orbital. So I write that structure and I'll show the formation of pi bonds. So after the formation of the sigma bond, we have this structure. Yeah. Yeah, we have already seen that in carbon and both in oxygen, there is one unhybridized p orbital with unpaired electron, and one unhybridized p orbital with pair of electrons. These unhybridized orbital forming pi bonds over here. So each carbon shape of the p orbital is dumbbell C, and all these unhybridized p orbitals are perpendicular to the plane of the sigma bonds. Okay, perpendicular to the plane of the sigma bonds, and each of the carbon unhybridized p orbital are having a single electron, unpaired electron. So just for our convenience, I can write the opposite spins. Yeah, and in case of oxygen, there is a pair of electron. The unhybridized p orbital of oxygen is containing a pair of electrons. is these orbitals are now showing an sideways overlapping or lateral overlapping. The upper lobe overlaps laterally or sideways. Here also upper lobe, lower lobe, upper lobe, lower lobe. Here also this upper lobe, lower lobe, lower lobe. Yes. This is the final molecular orbital structure of furan. Now you can see here the sigma bonds are already formed, and now these sideways overlapping are forming the pi bonds, the complete bonds. Here now we can see in this structure. This is the final structure of molecular orbital structure of furan. So you know the sigma bonds are always formed by head to head overlapping or in a axial overlapping, and pi bonds are formed by sideways overlapping. So this is the final structure. You know here carbon are all unhybridized p orbitals and oxygen unhybridized p orbital. Totally each carbon 4 electrons, and this one for oxygen, that is also forming giving a one pair of electron. The another pair is non-bonding, that is as it is. You can see here that does not forming any kind of bond. So in case of there are two orbitals in case of oxygen. One is hybridized, that is not forming any bond with a pair of electron, and there is also one unhybridized pair of orbital, p orbital, with a pair of electron that is forming a pi bond. So though here you can see 1 1 1 1 2. So each carbon is giving one electron and oxygen is giving two electrons. So totally there are 6 delocalizing electrons. 6 delocalizing electrons. So here you can see this is the molecular orbital structure. This is equivalent to here. You can see now carbon, oxygen. So our oxygen, there is a one lone pair. One of the pair involved in the bond formation, and one pair is not involved in the bond formation. And here there is a pi bond. Pi bond is forming, and each carbon is having a sigma bond with hydrogens. This is equal to this structure. Or you can write like this also. If you show the electron cloud, pi electron cloud, we can now completely mention all oxygen, and so like this you can write. Here I have shown the lone pair of electron that those involved, sorry, the pair of electron involved in the bond formation. Here I am not showing because I have shown the pi cloud. The pi cloud is containing these two electrons. The one pair is a lone pair, is non-bonding pair. That's why I am writing at the outside the ring. Okay, this is about the molecular orbital structure of furan. Students, usually the questions are framed like write the molecular orbital structure of furan and mention aromaticity. Usually the questions is asked along with the aromaticity. So that's why we'll see the aromaticity of furan now. To compare any compound, if it has to be aromatic, then it has to fulfill 4 criteria of aromaticity. So let us see one by one. The first criteria is the compound must be cyclic and planar. Cyclic and planar. In the case of furan, you know it is a ring structure. Ring means cyclic, so it fulfills the first one, and it is a planar in geometry. So as you seen in the molecular orbital structure, where it is a carbon and hydrogen, carbon and oxygen, all of them are undergone sp2 hybridized. sp2 hybridized means trigonal planar geometry. So it is also planar in nature. So the first criteria is completely fulfilled. When it comes to the second criteria is they must contain delocalization. They must show delocalization, or they must contain delocalized electrons. So there are totally 6 delocalized electrons in the case of furan. Delocalized pi electrons. If you see the structure of furan, as you've seen, So here, okay, these two pi electrons, this pair of electrons involving pi cloud. So totally 6 pi electrons are involved in delocalization. So this is nothing but resonance. This shows the resonance. We can see the resonance structures of a furan in when we discuss about the reactivity, when we discuss especially the electrophilic substitution reactions. If it is showing resonance, it definitely give us a conjugation system. It is a conjugated system. The conjugated system involving 6 pi electrons or 6 electrons. So this again fulfill the second criteria. It shows the resonance, or it involves it can show delocalization of electrons. So third criteria, when it comes to the third criteria, it should obey Huckel's 4n plus 2 pi electron rule. Pi electron rule. So Huckel's rule, what is Huckel's rule? The Huckel's rule is the cyclic planar structure, the completely conjugated system which containing 4n plus 2 pi electrons is aromatic in nature. So here n is the number of rings. If you put n equals to 1, so then 4 into 1 plus 2, that is equals to 6 pi electrons. So you have already seen here 6 pi electrons are there. According to Huckel's rule, the systems containing 2 usually not there, that cyclic, it should not be, it will not be cyclic. Hence 6 pi electrons, 10, 15, 18, these all will show aromaticity. Okay, these all will, it is so on still, these all show the aromaticity. Here we can see in furan 6 pi electrons, as you already seen. So hence it is also obeying the Huckel's rule, that is the third criteria of aromaticity. And when it comes to the fourth one, the compound should undergo electrophilic substitution, because for aromatic compound it is one of the characteristic property, electrophilic substitution reaction. For electrophilic substitution reaction is nothing but the replacement of the proton or hydrogen with an electrophile. So to replace that hydrogen, that compound must contain hydrogen atom. In case of furan, we know it's in its molecular formula, that is C4H4O. There are 4 hydrogen atoms. These 4 hydrogen atoms can be replaced by any electrophile. So hence it also obeys the fourth criteria. Hence when it obeys all the criteria, the first one is cyclic and planar nature, and it should have delocalized electrons, that is showing resonance and with the conjugated system. And third one is it should obey Huckel's 4n plus 2 pi electron rule, and it should have minimum at least one electron for the electrophilic substitution reaction. It obeys all these criteria. Hence furan is aromatic in nature. So this is about the molecular orbital structure of furan, and also we have mentioned its aromaticity. I hope you all understood. So thank you for watching, and please like the video, share with your friends, comment on it, and also subscribe the channel. And please hit the bell icon to get updates of my upcoming videos when they will be uploaded. Thank you.